Hi everyone, my name is Paweł and I'm here with Krystian today. We've got some hopefully exciting concepts in Niagara to show you and just show you a couple stuff that we've been working on in the past year. Our goal was to experiment with the Niagara. We also wanted to see how far we could push it and to build a simple logic and interactivity in our systems without touching the blueprints. So just to give you a little bit of background about myself, I've been working in the game industry for over 10 years now, and during this time I work on many projects, including those that have been cancelled and those that will be released in coming years. I enjoy working with companies such as Climax Studios, 505 Games, CD Projekt Red, Hi-Res, and now I'm working at People Can Fly. Also, in addition to my work in gaming, I also teach real-time VFX online. If you haven't heard about the vertex animation textures yet, I've got a few examples here. The ones with SB next to it use the soft body technique, which means the mesh needs to have the same number of vertices in all frames, and I personally think it's perfect for any objects that are textures and it doesn't change its topology during the animation. The R, on the other hand, use the dynamic remeshing method that mostly used with fluids and mesh morphing. To get a similar look without using vertex animation textures, you'll probably need a rigged model and animated. That's also a skeletal mesh in Unreal Engine. But those actually run on the CPU, so you can have good number of them, but I wouldn't go crazy with those animations. VATs, on the other hand, they used, what you can do, you can bake the animation into your texture files, and then each texture has saved the X, Y, and Z position of each vertices per frame, and those actually run on GPU. So you can put them into Niagara and spawn a bunch of those meshes in the scene. All you have to do, you have to just assemble those in a shader, and you can then run it on the GPU in Niagara. And that's going to allow you to have many of those objects in the scene real time. The initial setup can be a bit tricky if you haven't done anything with the vertex animation textures yet. But once you get a hang of it, you'll start noticing other places where you can actually start using vertex animation textures, as it's just friendly for the performance. So if you want to learn more about VATs, how to create and import them into the game engine, I'll highly recommend this guide by Simon from SideFX. I think it's just excellent starting point for anyone who hasn't done anything with vertex animation textures yet. In the next slide, I actually want to show you what I've been working on after testing every single method of the vertex animation textures. So in here, I wanted to create a hostile plant that could interact with the character. And to achieve this, I use an animated mesh, turn that into a vertex animation texture mesh in Houdini. And the main reason for this was that I actually wanted to have loads of those plants in the scene. And I didn't want to sacrifice the performance because I believe that performance can be used for something else, like a really good AI system, for example. And this allowed me to have a bunch of those with a very simple logic in Niagara. As I work on the project, I discovered that I could control the animation states of the plants in the particle system. I was just curious how far I can push myself and what I could create with the very basic setups without using blueprints at all. So let me show you step-by-step approach so you could maybe start creating your own vertex animation setups. So to start off, we need an animated mesh, and we can just put it in Houdini and export it as a vertex animation texture mesh. But it's important to work with your animator to keep the number of frames as low as possible. So that's gonna give you very nice texture resolution. It's also crucial to work with a 3D artist to keep the vertices on your mesh low. However, I did want to push this idea a little bit, so this mesh actually has 16,000 vertices. And as a result, I have 5 animations there. There's an idle loop. I also got the exit from the ground, loopable run, attack that's going to include the plant exploding, and the replant in case player will get too far away from the plant, so the plant can go back into the ground. And you can see the examples of the texture, how they look like in the engine at the bottom of the slide. So if you want to control animation states in Niagara, there are probably many ways to do it, and each of us VFX artists would do it differently. I found the effective way is to use enums. So to get started, you have to create an enum file in your content browser. There you can put the text. In the text fields, you can put your animation states. And after that, all you have to do is just put it into under plugins Niagara and into your enum. So you can, or alternatively, you can just drag and drop your enum file into the scratchpad. And once you've done that, you can find your enums there in the map-get section in scratchpad. To choose correct frames, you could have floats. Just make sure you're setting your frames using dynamic parameter in the material. And with these steps, you'll be able to have your animations and control them manually in Niagara. So once you've done that, you can exit the scratchpad, turn your floats that you created, and select the frame ranges. And also you can just turn that into user parameter in Niagara so you can control those in blueprints if you want to create a logic. Personally, I wanted to continue in Niagara just to push myself because mainly this task was for me to learn a lot more about the scratchpad. So I decided I'm not going to be using blueprints at all. So when it comes to switching animation states automatically rather than manually, I found that calculating distance from the camera worked best in my case. I used a node called camera query with get properties to read the camera position. And based on that value, I was able to switch between the animation states if player will get close to the plant. I gotta say, enums were very helpful, but I needed additional ints and bools to control various states. It was a bit painful, especially if you wanted to have a bit more states. My suggestion would be to start with a very simple logic in Blueprint, and once you are happy with the logic that you've made there, you could see if you can transfer it into the scratchpad if you just want to use Niagara. The simple logic to actually move plants towards the player, I use lerp. I got the camera position and calculated the distance between the camera and the particle position. To control the speed of the particle movement, you can create your own variable, float, and then multiply that float with delta time. And that will be your alpha value for your lerp. And then simply activate your lerp if the plant is in the run state. Also adding move to distance field node in Niagara will help you keep your model grounded. So it's not going to be floating in the air. And currently there is no self-collision implemented yet, but I think this method works great for simple movement concept. And personally, I'll start simple to see if it works, and if it does, then you can see if you can add some layering on top to create a bit more complex system. So when I was working on it, I think it was the time to, because once I figure out the animation state, I wanted to add some visual effects to the plant. So I wanted to have a glowing spores when it was in the idle and running. I wanted the liquid explosion and the cloud spores for the AoE, and the dust while it was running towards the player. And for those effects that were constant, like dust and spores, you could use a data instance alive node in the scratchpad, and that's going to allow you to turn the particles on and off. However, for the explosion, it was a bit tricky because it requires the burst instead of spawn rate. And fortunately, my friend, work colleague Michał, he helped me with that one. And he just reminded me that we can open any module that is in a Niagara system just to see how they work. But yeah, just make sure whenever you'll be tweaking one of the Epic modules, just duplicate them first, otherwise you're just going to override them. So let me show you the plant example one more time. I just hope it's going to inspire you maybe to try to create your own vertex animation texture system yourself. I've seen many of them, and I'm always amazed what's possible with Niagara, especially if you combine that with software like Houdini. For me personally, the next step would be to create maybe a collision system or separate module So upon explosion, we could damage the player. Another idea I actually want to try, once I get back to it, would be to, instead of damaging the player, I could have a bunch of minions running with the player and maybe destroying the enemies. I did stress test as well, just to see how many plants I could fit into a single scene. And it turns out that once I got between 5 and 10,000 plants, the frame rate would start to drop. So I'm not sure if that was because the mesh had 16,000 vertices, or if there's maybe some room for improvement in my scratch pads. But the biggest issue I've encountered with it was that the bounce of the GPU system, because if the camera vector is facing away or it's outside of those bounds, the system would disappear instantly. I think it might be a good idea maybe to put some larger values into the bounds and just balance them against the performance. But of course, it depends on kind of game you are working on. I also noticed in the recent version of Unreal Engine, there is something like dynamic bounds, but I haven't tested them yet. And there are a bunch of other ways that you could use those methods. Lots of studio already started using them for insects, birds, or even a distant army or crowds. Hopefully we'll see more creative uses in the future. If you have any questions after, I'm just happy to help, and I can walk you through specific steps of the plan setup if you want, or answer any questions. I just want to also to give credit to people who helped me with this plan setup and throughout the process of making it. That's it for me, and Krystian next hopefully is going to blow your mind with his example. Thank you.
So, hi everyone. My name is Krystian Borowski, and I am a visual effects artist at People Can Fly. And yeah, in this part of presentation, we will delve into the principles, techniques, and possibilities that lie within this fascinating domain of building interactive visual effects. And we will examine the underlying solutions that enable these effects to come to life. But before we do so, let us take a moment to understand what exactly these interactive visual effects entail by playing the short intro. So this will play in the background, but a couple words about this visual effect until we dive into the details. This effect you just saw is an integrated and interactive Niagara system, and it combines various elements into a single piece that can be instantiated at different locations. And this system encompasses everything from player ability effects to object destruction as well, seamlessly adapting to specific circumstances. And through this unified framework, let's say, players can engage with the object using different powers and abilities, enhancing the overall experience. So you can imagine that you can have, for example, the one player that will interact with this destructible object in this way with these wires, and another maybe will cast some magic spells to destroy it or do something else, and everything is integrated in one Niagara system. And yeah, in summary, what you saw is a testament to the power of integrated design, where multiple elements converge to create a dynamic and immersive visual effect system. And the objective of this part of presentation is to provide you with valuable insights on approaching the construction of these systems. And while they may be perceived as hard, as complex to build, I assure you that it doesn't have to be that way. And this is one of the main goals of this presentation, to show you that you can build actually these effects. You can start building these effects, you know, after seeing how they actually are built from the scratch. So, as I said, it's easy to feel overwhelmed at the beginning by the grand vision of what you want your system to achieve. And to avoid this, it is wise to begin with small building blocks and focusing on functionality first, and leaving the visual aspects for later stages of development. And by adopting this approach, you can effectively manage the complexity and ensure a solid foundation for your system. And this step-by-step process allows you to refine and iterate on the functionality before diving into visual aesthetics, resulting in a more streamlined and successful implementation. So let's embrace this methodology and embark on this short journey of systematic development, starting from the core functionality of this system and gradually waving in the visuals. So starting central to our system are two essential objects, right? We have a source and a target, and you can think of the target as this vase that you saw on the intro, and source can be a player or other object that interacts with this object, right? You can, because instead of a player, you can also set the enemies, for example, to interact with it. And yeah, we have these two objects, and here you can see the red dot, which represents the target, and the white dot, which represents the player position at this stage. But for now, you can think of this red dot as a Niagara system, and this white dot is just the player position for our information. And going forward, we set the position of the source particle to the player position. So we have two particles right now, and but we don't know much about them in space. So we need to take some information about the relation between these two in 3D space, right? So going forward, as I said, we are starting from very basic. So we need to calculate a vector pointing from source to the target, and this vector can give us some valuable data about the relation between them in space, right? So here's how you would do it in Niagara. You just subtract one vector from another, and you take the properties of this vector. And there are only two properties, right, that we are interested in. This is the normalized vector, which is the direction, and the length, which will give us information about the distance between these two objects. And so now we have the direction pointing from the target, which dynamically updates, because we are doing these calculations in update tick inside Niagara. So it will always gives us the result of the distance and direction at current frame, right? And that's something good to start, so well, let's go ahead. And now we are starting diving a little into those interaction topics. So an interaction always happens based on some condition, right? If you want to invoke specific behavior, you need to specify it. And there are multiple options to choose, but in this case, we can use the distance-based condition. You can also use a time-based condition, for example, but in this case, we are going with the distance. So we create the activation distance out parameter of type flow that you can see on the right up corner. And this parameter will specify a specific distance value from the target. And you can see this distance actually marked by the red circle, but it doesn't do anything for now. It's just a value that gives us some information. And here you can see how we are utilizing this distance. And as a condition to dynamically change the position of the source between the player and the target position. So you can see that the source position is set to the player position, but only if the player reaches that red area. So we can say that we implemented this way that the Niagara and this interaction doesn't work, doesn't always calculate those player properties. We only enable it when a player reaches this area. And yeah, going forward, we can make it more interesting by adding a second parameter, which will specify second distance from the target, which is marked by the yellow circle on the screen. And we can call it, in this example, activation distance, just that you can, for you can refer how it works. And here you can see that we can use these two distance parameters, distance attributes that we created to create the remapped range value that will go from 0 to 1 between those two circles. So if I go forward, we can say that near the red circle, we will have the value of 1, and near the yellow circle, there will be a value of 1. Sorry, it's reversed. In the red circle is 0 and yellow is 1, and all between interpolates, right? So going forward, in this scenario, the target particle scale is interpolated using this normalized range value that I was talking about. And the size interpolates between some default value and the size of the inner yellow circle. And as I said, you can see that the source is going between this yellow and red circle, and this value basically drives the size of this source particle, right, a target particle. And we can also use this range value to interpolate the source line endpoint position between the source itself and the target. So here you can see that we are, in general, driving this endpoint that will be used to as an endpoint for the wire itself. And if I go to the next slide, here you can see how it actually works. We have really basic functionality of this attachment that you saw on the intro, right? And as I said, we are only using the distance-based condition, but we also can upgrade it to make it time-based condition. So if the source, for example, reaches the red area, we can activate some timer. And in this way, we will attach this endpoint to the target based on time as well. So knowing that the distance marked by the yellow circle gives us the clue that the target is reached, we can utilize it as a condition to invoke many other behaviors on the target or even the source. And here you can see that some forces are applied to this target particle as soon as the source reaches the inner area, right? Because we know that this parameter, this remapped range that I was showing you previously, has a value of 1 when the source reaches this yellow area, right? And here you can see how this solution was implemented for the system that you've seen previously. And here you can see that the forces are being applied to the target, right? Because the target are the vases, the vase parts, as well as some shader operations are being made on this, and as well as the wire behaves in a slightly different way as soon as the wire attached to the piece, basically, to make it more aggressive. And yeah, and this movie shows, for example, how this range was used to interpolate scale value from the attachment near the mesh at the end of the wire, and there are two mesh renderers. So you can see that in this example we have this device closed, right, and it scales down near the target. And if I go to the next slide, here you can see that we have another mesh renderer that scales up near the target. So it does the reverse thing that this one in the previous. So all of this combined gives us the illusion that the device is being opened, right? And you can also use the same technique that Pawel was talking about in such scenarios. You can make a VAT texture and drive this VAT texture animation using this parameter, right? This interpolation parameter. But in this scenario, for example, it all happens so fast that I thought that you can use such a solution, for example. And we've talked about how to set basic interactivity between particles. So now let's see how we can build the wire connection between them. And so we start by dividing the distance between the target and source, right? Because we want to have a lot of parts in general. And we specify some parameter, in this case called segments. So if you divide, for example, this distance between source and target by 10, you will have 10 parts, right? So it's quite simple, but here you can see, of course, how this can be implemented in Niagara. I am showing this because it's quite important to promote this segments parameter to some up values along the chain to scale it later. So because we want to build a dynamic system, right, that will adapt to different scenarios, and we want to have ability to change it along the way, along the development. So here you can see, for example, that we are changing the number of segments, right, and everything updates. So it's kind of simple, but you have an idea of how it works. And here, of course, if you change the source, it all updates. And yeah, now to distribute particles along the line, we can multiply the particle ID by the segment length. So it will give us proper offset value for each particle. So you can imagine that we have, for example, particle with ID 0. And if you multiply 0 with segment length, you will have 0, right? But if you multiply 5, you will have the point, the midpoint between source and target, and it will update at every frame, right? And referring to this pseudocode that you can see here, it's now in specific programming language, because I know that some of you, have background in scripting and programming, but some of you want to prefer working with nodes. I tried to make it plain English so everyone can have kind of understanding, right? And here is the representation of this in Niagara, right? So we have this offset value, we multiply it by particle ID, and then we multiply it with the direction, right, between source and target. And then we add this to the source location to calculate the final position on the line. And for the system to fully adapt to target count, the attribute reader can be utilized to get the number of particles from the target. So you can see we have a particle attribute reader. And for those of you who doesn't use Niagara, attribute reader allows you to take parameter values from different emitters, right? Pawel showed you, for example, his system was built from different emitters, right? You saw these blocks with orange block at the top. So one emitter can read some values from another, and in this case we are taking the number of particles from the target emitter. So this way we can change dynamically the number of segments on the line, right? Referring to the target. And of course, you can see that we have this spawn count binded with these nonparticles. That's how we actually do that, this dynamic spawning. And here you can see how changing the segments value have an effect on the number of particles spawned. It's kind of simple, but I'm showing step by step, so that's how it works. So here you can see the source target direction, which is marked by the yellow arrow. And we have also a vector pointing up, and by calculating the cross product between this yellow arrow and up vector, we have this green arrow, right? This is the cross product between these two, and we will use this this direction as a movement for our wire, right? So going forward, before we add movement in general based on this sine wave, we need some angle value that we can specify for the sine function, right? And instead of using time, the parameter called sine angle is created in Niagara. And in every update, the delta time multiplied by the speed float is added to this sine angle. So you can have a sine angle parameter that will go faster in some periods of time, because as you can see, if you change the input speed to 0 for example 30 update ticks, the sine angle won't increase, right? So your sine will stay in place, right? Because it won't work on this period. And you can't do it with time, because if you stretch the time for some period of time, you can't make it back without going through all the time that was skipped again, right? And yeah, to achieve the wave movement, we need to create the remapped range of the particle ID. And if we add this range to the sine angle and use the result as an input value for the sine function, we will have a slightly different result for each particle. And here you can see, right? Because if we use this sine angle with the same value for each particle, all particles would move at the same speed, so entire line will move. But by adding this remapped range, we slightly differentiate this input for the sine wave for each particle, right? And we can create even more interesting movement by rotating the previously calculated cross product, which was marked by the green arrows. So we are using the rotate angle on axis, which I will show you in a minute. In general, it works this way, that you have, for example, this direction from source to target, which is marked by the yellow arrow, right? And we are rotating this green direction on this yellow arrow by some degree. And in this example, you can see that all the particles have the same value for this rotation. So here is this rotate angle on axis in Niagara. And to make it more interesting, right, we create a similar approach that in previous step we are creating the remapped range of the particle ID, which is going from 0 to 1, and you can see this on this gradient that goes from red to blue, right? You can imagine that the red value represents the 0 value and the blue one represents the 1 value. So if we add this to this angle that drives the rotate angle axis, each particle will have slightly different this parameter, right? And it will result in slightly different rotation for each particle, right? So we can make some twist operation using this. And here you can see how it is implemented in Niagara, right? Here you can see this twist parameter that I was talking about. So you can manipulate this twist strength, and the entire sine wave will twist more or less. And here's the same construction, but from slightly different angles. So you have kind of an idea how it looks like in 3D space. And here you can see the scalability of the system, right, based on the target or source position change. Because we build this functionality on this, that everything updates in update tick. When you change something, the sine wave also changes, right? And here, of course, when you change the number of particles, you can see that how the sine wave behaves. Because we have more particles, the remapped range have more resolution, let's say, right? And yeah, if you look now for the particles that move near the extreme points of this line, I mean that you can see, for example, near the source here for the particle 0, it still moves, right? But we don't want movement in this place, because we want to simulate this attachment that you saw on the intro, right? So we can create another remapped range, but in this case, this remapped range is constructed in such a way that you can imagine, you can see this gradient, right? That these particles, this color that goes from green to the purple, right? And you can imagine that all the values that have value 0 are marked by green, and all the values that have value of 1 are marked by the purple color. So right, so if you multiply this wave offset by 0, you will have no offset, right? And all gradually moving toward the middle, you will increase this movement, right? So here you can see how it works actually. And this is how you can construct such a gradient in Niagara. You have one remap range for the source point, right? Near the source, near the first point of the wire. For example, going from 0 to 0.3 to 30% of the length of entire wire. And another does the same, but from reversed perspective, you know, so from 70% to 100%. And if you multiply these gradients together, you will have this, right? This gradient that is marked by this purple and green color. So going next to properly render the geometry for the segments, we need an orientation along the curve. For now, you can see that particles doesn't have it, so all are pointing in some default direction, let's say, that is marked by these yellow arrows, right? And to achieve that, all the logic for the particle placement that I was talking previously is packed into the Niagara function, right? So it's all I talked about minutes before. We are packing it into the function, and then this function can be used to sample next position on the wire, right? Instead of using attribute reader when we read the particle data from the system that everything is implemented, right? We can have this function to sample next position on the wire just by adding a 1 to the current current particle ID that is being processed. And yeah, then we can just subtract the two positions, and this will give us the direction between one particle and the next on the chain. And this is how it looks like when we apply, for example, some simple cylinder to these particles. You can see that when you change the number of those segments, the resolution of the line changes, right? And also the scale, the segment length parameter that I was showing you previously is used to scale the single cylinder, right? So it will always stretch between one segment and another. And going back to the sine angle parameter, this is it was used as an input to drive the sine function, right? And the speed input can be increased for a small period of time. This is what I was talking about, right? Instead of simulating physics and doing all those, hard computations, we can, for a small period of time, increase the speed that is that is being multiplied with the delta time, and in this case, the sine wave will move faster for a small period of time. And we are doing it with many different parameters, with scale of the offset as well. So it gives more interesting reaction behavior. And here you can see how scaling multiple values influences these particles under the hood, right? And here, having the wire created, we can utilize the previously described technique for this attachment, right? So this is the same that I showed at the first slide. You can just think of this purple circle as a player, for example, right? So this is the base functionality for this attachment system. And here we can, of course, change the wave properties during this attachment event, right? So, for example, we can set a timer when the player reaches this yellow circle that I was showing you previously, right? For example, for, I don't know, 10% of a second, and change these values for some time. So we have this different behavior. And for now, we were working with just one line. So to dynamically adapt the system to different target count, the module of particle ID with the segments can be calculated, right, to produce the looping value going from 0 to the segments. And to set different targets for specific connection chains, we can divide the particle ID by the number of segments. And then this values can be used as an input to sample wire position function that I was showing you previously. And here you can see it in Niagara, right? And going to more complex stuff, more interesting, I can say, right? I want to talk about the concept of object library in Niagara, which allows for dynamic changes of specific grouped values based on the input value or some runtime conditions, external conditions, let's say. And for example, if we want to have multiple target objects, let's say, in this case, this will be a sphere, a torus, and a cube, for example, right? The properties we are interested in are the fractured mesh parts and position data for particles. And we can design a system that will bind selection of these properties with some input. So going forward, here you can see that by changing the object ID parameter, we are able to dynamically choose different constructions for specific objects, right? And we are doing it inside one Niagara system. Normally, some people will approach this that they will copy the entire system inside the engine, right, and create another input data. But you can actually implement it in Niagara, right? You can have a library of objects and you can feed this system with different data to reproduce this. And here you can see how it is actually done. It's quite simple because you have input arrays, right, of vector data. And you have, for example, a box data. If the box is made from five parts, let's say, you have 5 particles for this, right? And you just get the value from the array by particle index because you know that we have as many particles as are the target parts. So here you can see that we are taking the length of each array of this input to drive number of particles, right? And here you can see how the entry looks like. We have just an array of vectors, as I said. How we do it, actually you can make it manually if you want from Houdini, for example, but in this case we created some tool that we can, because it's just the data, right? If you, for example, fracture the mesh in Houdini and the mesh is fractured to 10 parts, you can take a position of each part and you can take this here. And how you can do it, it's you know, your own choice, but having this data, you can have this library of objects, right? And here you can see the render, how it actually looks like for the vases, for example. And I don't know if all of you will see this, but at the bottom is the renderer visibility parameter, and is set to 1 for the vases, for example. But if I go forward, here you can see the render for the concrete barrier, right? And this has the render visibility value of 2. So if the object ID is set to 1, for example, the vases won't be rendered, right? But when it's set to 2, the concrete barrier will be rendered, but the vases won't. So here is how the binding of object ID with the visibility tag looks like, right? We have just this object ID, and we connect it to the visibility tag, which is connected to this visibility tag right here. And the object library also drives the selection of that values that are used to drive the simulation of the objects, and such solution gives us an option to completely change the behavior of the particles based on the selected object or some external condition. So you can see, for example, how the input for the forces looks like, right? We have different force inputs for different parameters. And here you can see how the selection of an object works on the instantiated system, right? You can just copy the entire system. You change the object ID and you have totally different object constructed, right, with different properties. And here you can see there are two instances of the same system. And notice that the cones behave in a slightly different way than the vases, right? The vases have spawned these particles of debris, for example, but the cones doesn't have it, right? And you don't need to copy the system and change those properties in the emitters that, for example, Pawel was showing you. You can just implement this logic in this object library, right, to dynamically change these properties. And this slide shows how you can actually change any Niagara exposed parameters inside the blueprint, right? I just wanted to show you. And going to the rendering wire, the wire is a construction of multiple renderers combined together by using multiple gradients of values between 0 and 1. This is the same that I was showing you previously with these gradient values. And here you can see that, for example, we have one layer with sprites. If I go forward, here you can see that we have, for example, we have a mesh layer with you can imagine that we have, in this example, gradient that have the bigger value at the tip, goes to 0 for some period of time, and then increases again. So we have this interesting shape. And in the same method, we create these leaves, for example, let's say, and the chain. And all of this combined creates a more interesting shape than just the sprites, right? And here we are. We have gone through the process of creating the functional interactive system. And as you can see, creating such system doesn't have to be complicated. By starting with simple framework, let's say, and gradually expanding upon it, we can develop a solid foundation that drives this entire system, right? We started only with 2 particles, and we finished with implementation, let's say, of some object library that we can utilize to different scenarios. And thanks, that's all from my side. I hope now you have a better understanding of how to approach building such systems. And now together with Pawel, we'll have a couple of minutes to answer your questions. So thank you.
Thank you for this dose of knowledge. Truly, we don't have so much time, but I see we have time for one question. So there is any questions? Please walk up to the microphone.
Thank you for a great explanation of that subject. I got a question according the implementing meshes to ribbon. How did you get it? Did you implement it directly in Niagara, or did you implement it?
Yes, it was entirely implemented in Niagara.
Okay.
It works in this way that I was showing you, for example, this division of the line into segments, right?
Mm-hmm.
So if you have one particle at a specific segment and you have another one next, right?
Mm-hmm.
And then you compute the direction between these two, right? So when the sine wave moves, you have always this direction pointing to the next particle, right?
Yeah, but I'm rather asking about the meshes.
Yeah, I'm going
yes.
toward it, right? Because
how did you achieve that smooth layer between the spline and meshes? Did you use just only Niagara system?
Yes, it's entirely Niagara, but you are asking about the smoothing of it. It depends on the resolution of the line, right? Because I was showing that you can have the line constructed from 20 particles, let's say. So this way, the wire will be smoother, right? Mm-hmm. The transition between, you won't notice the difference between one particle and another, because the particle, one segment doesn't bend, right? It's always static. And if you increase the resolution of the line, you have more, let's say, these cylinders, right? Yeah, and then you won't notice the difference between interpolation, right? If it's answer your questions, I don't know.
Okay.
Yeah?
Thanks.
Thanks.
Thank you.